James Webb found a planet with 99.7% chance of life. Hidden within the constellation Leo, roughly 120 light-years from our planet, a telescope has captured something that may permanently reshape everything humanity believed it knew about life in the cosmos. The James Webb Space Telescope has identified a world where surface temperatures hover consistently around 49 degrees Celsius, or about 120 degrees Fahrenheit, enclosed within an atmosphere that pulses with the chemical fingerprints of living organisms. Scientists place the confidence level at 99.7%. A planet potentially breathing with life, one that could be even more hospitable than Earth itself. If you find yourself drawn to the strangest and most awe-inspiring discoveries in space, hit the like button, subscribe, and let us dive in together. What arrived at our instruments did not look remarkable at first glance. It came as a pattern encoded in light. Faint distortions, almost invisible, concealed within the glow of a faraway red star, captured by the James Webb Space Telescope and slowly unfolded on computer screens by scientists trained to decode the universe from incomplete fragments. There was no image of alien seas. There was no photograph of strange clouds drifting above unknown coastlines. There was no outline of another world's geography. Only data existed, only starlight, and yet inside that narrow stream of infrared radiation was a possibility so immense it seemed to alter the very meaning of the night sky above us. The world responsible for that signal is known as K218b. It is a planet orbiting a dim red dwarf star inside the constellation Leo, more than 100 light-years from Earth. It is larger than our planet and considerably heavier. Not quite a second Earth in the traditional sense, but something far stranger. Something suspended between categories we already understand and categories we are only beginning to define. For years, astronomers treated planets of this type with cautious skepticism. They appeared too massive to be comfortably Earth-like, yet too small to qualify as genuine gas giants wrapped in the thick atmospheres that such large worlds usually carry. At first glance, they seemed too deep and too alien for life to realistically take hold. That assumption was reasonable. Human imagination almost always begins with the familiar. When we picture a world that might support life, we instinctively picture some variation of home. Blue skies, shallow oceans, rocky continents, clouds drifting beneath a sun much like our own. We construct our idea of habitability the way an architect begins, with a single familiar design. But the universe rarely commits to repeating one blueprint forever. Again and again, it takes the structures we assume are fundamental and reveals them to be only one possibility among an enormous range of alternatives. This planet did not fit the old image of a world capable of sustaining life, and that is precisely why it became impossible for scientists to ignore. Webb did not observe K218b directly. Instead, it watched the star that lies behind the planet from our perspective. Each time the planet crossed in front of its host star during its orbit, a fraction of starlight passed through the planet's outer atmosphere before continuing its journey across the vacuum of space toward Earth. The gases within that atmosphere absorbed certain wavelengths of light and allowed others to pass through undisturbed, leaving behind a subtle pattern of missing colors so delicate it could easily be dismissed as random noise. But when the telescope is precise enough and the analysis is sufficiently careful, those absences become meaningful evidence. It is somewhat like identifying a traveler not by catching a direct glimpse of the person, but by studying footprints left behind in freshly fallen snow. An atmosphere reveals its chemical contents not by what it displays, but by what it quietly removes from the light passing through it. This is how astronomers began constructing a portrait of this distant world. First came signs of carbon-bearing molecules drifting within the atmospheric layers, then water vapor, then methane and carbon dioxide. None of these gases alone constitute proof of life, but taken together they point toward a world with active and ongoing chemistry, and a sufficiently complex climate to sustain scientific attention. The picture remained incomplete, still surrounded by active debate, still wrapped carefully in the caution that serious science demands. But it no longer felt empty or without meaning. The planet had begun to shift in the human imagination from a distant abstract point in a star catalogue to something that felt more like a real environment with genuine conditions and genuine processes operating within it. And then came the molecule that electrified the entire story: dimethyl sulfide. On Earth, dimethyl sulfide is closely associated with biological activity, particularly with microscopic marine organisms living in the upper layers of the ocean. It drifts upward from living seas into the atmosphere, above like a faint but measurable chemical trace, the kind of signal produced not by any single creature, but by vast interconnected systems of organisms functioning together. You do not directly observe the organisms themselves through this kind of atmospheric signature. You observe the chemical exhale of their collective existence. That is what made the possible detection of this compound in an alien atmosphere so arresting and significant. If dimethyl sulfide, or a closely related molecule, was genuinely present in the atmosphere of this distant world, then the nature of the discovery shifted in a fundamental way. The question would no longer be whether the planet might theoretically support life under certain favorable conditions. The question would instead become whether something alive might already be present there, quietly and continuously altering the chemistry of an alien's skies, without any awareness that anyone was paying attention. This is where scientific wonder and careful caution meet each other directly. Astronomy is a discipline shaped profoundly by the challenge of distance, and distance has a long history of being deceptive. A signal that seems clear and compelling in one dataset may weaken significantly or disappear entirely under more rigorous analysis. One molecule can sometimes mimic the spectral signature of a different molecule. Statistical patterns can emerge from random noise and then vanish the moment a stricter analytical framework is applied. The universe does not surrender its truths easily or generously. It demands that we earn them through persistent effort and sustained skepticism. And so, while dramatic headlines raced towards certainty, the science itself remained considerably more measured in its claims. The signal was exciting. It was perhaps historically significant, but it was not final. It was a strong and compelling hint, not a confirmed verdict. A door that appeared to be opening, not yet the room that lay beyond it. Even so, the scale of what this moment represents is genuinely difficult to overstate. A telescope built by human hands, now floating in the deep cold of space, has become sensitive enough to read the chemical composition of the atmosphere of a world more than a century of light travel away. It does not land there. It does not descend through alien clouds or dip instruments into alien seas. It studies tiny, almost imperceptible gaps in the spectrum of a distant star, and from those gaps it begins to reconstruct weather patterns, gas compositions, atmospheric pressure gradients, and perhaps even the first faint traces of biology operating at a planetary scale. There is something almost poetic in the restraint of that method. Humanity is not conquering this distant world. It is listening to it. If current interpretations prove to be at least partially correct, this may be an ocean world concealed beneath a thick, hydrogen-rich atmosphere, with pressure building steadily downward through layer after layer of haze and vapor until the familiar distinction between sky and sea becomes something far more ambiguous. Earth offered us one version of what a living planet can look like. This distant world may be suggesting something entirely different, not a copy of home, but a completely different architecture achieving a different kind of balance. That distinction matters enormously, because it widens the conceptual map of where life might realistically be found. For decades, the search for life beyond Earth followed a sensible but quite narrow path. Look for rocky planets. Look for temperatures similar to those on Earth. Look for stars resembling our own sun. Look for worlds familiar enough that we could imagine ourselves surviving on their surfaces. Those were reasonable starting points, because Earth remains the only inhabited world we know with certainty. But any starting point can become a limiting assumption if held too rigidly and for too long. Above all of this hangs the extraordinary weight of time. The light that Webb studied when observing K2-18b left that distant world more than 100 years ago. When those photons began their long journey across the cosmos, humanity was still learning how to fly. The modern technological age was barely beginning. Entire chapters of human history had not yet unfolded. While that faint beam of light crossed the enormous gulf between stars, generations were born and died here on Earth. Cities were built, nations rose and fell, and wars of unprecedented scale came and ended. Only now has that ancient message finally arrived at our instruments, carrying within its spectrum the chemical imprint of another world's atmosphere as it existed more than a century ago. What we are studying, therefore, is not the present state of that world. It is the past. The air we are analyzing belonged to K2-18b as it was when our great-grandparents were alive. If something biological shaped that chemistry during that era, the signal we are now receiving is ancient by any human standard. It is an echo from a time before rockets existed, before electronic computers were invented, before our species had developed the tools needed to even ask these questions in a rigorous scientific way. And yet the implication of that signal reaches directly into the present moment. If life was active there then, it may still be active now, continuing beneath alien clouds while we are only beginning to comprehend what we have detected across the vast silence between stars. At the center of this planetary system burns a star so small and faint that by the dramatic standards of stellar brightness it would barely merit a second glance. It is a red dwarf, cooler than our sun, dimmer, quieter, and far less radiant. If our own star is a blazing industrial furnace, this one is closer to a buried ember, glowing with slow and stubborn heat rather than spectacular intensity. It does not flood the surrounding space with brilliance. It simply endures year after year, century after century, millennium after millennium. Red dwarfs are by far the most common type of star in the Milky Way. They are scattered throughout the galaxy like countless small flames, easy to overlook because none of them dominates the sky the way larger and brighter stars do. For a long time, many astronomers regarded these dim stars with genuine suspicion when it came to questions of whether they could host inhabited worlds. Their habitable zones sit very close to the star itself, forcing any planet warm enough for liquid water to orbit at a distance that once seemed dangerously close. A world tucked that tightly around its sun might be scorched by intense radiation bursts, battered constantly by stellar flares, or locked permanently into a single orientation with one hemisphere, baking in endless daylight while the other froze in permanent darkness. Initially, those seemed like potentially fatal obstacles. But the deeper astronomy looks into these systems with increasingly sophisticated instruments, the more these dim stars begin to appear not as obstacles to life, but as genuine opportunities. K2-18b completes one full orbit in only about 33 Earth days. An entire year on that world passes before we finish a single calendar month. Yet despite that orbital closeness, the star is so restrained in its output, compared to our sun, that this world may still sit within a range of conditions that allows for a stable, long-lived atmosphere and potentially even the presence of liquid water somewhere within its structure. Distance in astronomy means very little without the crucial context of how much energy the star actually produces. A planet can orbit close to its host star and still remain temperate if the fire it circles happens to be modest enough. Red dwarfs also offer something that larger and more luminous stars fundamentally cannot provide. They burn their nuclear fuel with extraordinary patience. Where stars like our sun have active lifetimes of roughly 10 billion years, A red dwarf can sustain its steady output not merely for billions of years, but potentially for trillions. In the grand context of cosmic time, they are not brief candles that burn brilliantly and die young. They are hearths that radiate steadily through intervals so vast they barely have meaning at the human scale. For life, if life does emerge around such a star, time is the most valuable resource available. Given sufficient time, chemistry experiments with itself. Molecules combine in unsuccessful configurations, break apart, and recombine in new arrangements. Slowly, over immense spans, combinations emerge that can preserve and replicate themselves. Given still more time, those self-replicating molecular structures begin to compete, adapt, and diversify into increasingly complex forms. What appears absolutely impossible within a million years may become essentially inevitable across a billion. Around a quiet red dwarf, evolution would not need to race against a shortening stellar clock. It could unfold with immense and unhurried patience, like a river carving through bedrock, not through violent force, but through the relentless persistence of time. The atmosphere of K218b is the key to everything we currently think we know about this world, and the source of everything we remain uncertain about. It is simultaneously the layer that conceals the surface below and reveals its presence through the chemistry it carries upward into space. All of our current knowledge about this planet comes through that atmospheric veil, not through photographs taken by an orbiting probe, not through instruments descending into alien clouds, not through any lander touching an alien shore, but through starlight that has passed through the outermost chemical layers of that distant air and carried their signature across more than 100 light years to our telescopes. The atmosphere is both mask and messenger at once. It hides whatever lies beneath it, yet it carries chemical traces of everything that happens below, lifting molecules upward like fragments of a story encoded in a language we are only now beginning to learn how to read. The atmosphere seems thick and rich in hydrogen, layered with gases that suggest ongoing chemical complexity rather than the settled stillness of a geologically dead world. On our own planet, we rarely think of air as a structure with weight and depth. It feels nearly invisible, almost incidental to daily existence. But on a world like K218b, the atmosphere may function less like a thin protective shell and more like an ocean turned inside out. Deep, massive, dynamic, pressing downward with considerable force, actively governing the climate and the chemistry of the entire world. A thin atmosphere can only moderate the extremes of a world to a limited degree. A deep and massive one can govern it completely. The hydrogen-rich atmosphere detected around this distant planet may serve as a vast natural insulating layer, holding in warmth generated near the surface and redistributing it across the globe. What sounds threatening and hostile in the abstract may actually be the precise reason that some form of persistent balance is achievable there at all. Beneath that immense sky, there may be an ocean of some kind. Not an ocean resembling the blue sunlit seas we know from Earth, but something far stranger. A deep planetary body of liquid hidden far below layer upon layer of haze, cloud, and mounting pressure, existing in conditions so different from anything on our world that the boundary between the gaseous atmosphere above and the liquid ocean below might feel less like a clear surface and more like a gradual descent into increasing density. On Earth, the edge of the ocean is unambiguous. Here, the transition may be something more diffuse. Atmosphere blending into mist, mist thickening into cloud, cloud giving way to increasing pressure, and pressure eventually becoming something that behaves more like liquid than gas. Imagine descending into that atmosphere, not falling through ordinary empty air, but entering a vast vertical landscape with structure and character at every level. Upper haze layers glowing in dim reddish light far above. Deeper cloud decks rolling below like mobile continents made of vapor. Pressure increasing steadily with every kilometer of descent. temperature shifting slowly through gradients rather than jumping abruptly between extremes. Somewhere far below, perhaps an ocean receiving the filtered and transformed light of a distant star that has passed through kilometers of atmospheric layers before touching anything at the surface. It would be a world defined by transitions rather than sharp boundaries. No clear blue sky above, no simple horizon below, only gradual thresholds where one condition gives way to another, and somewhere within those gradual transitions, perhaps the chemical conditions necessary for life to take hold and persist. If such an ocean exists beneath those clouds, it would be the primary engine driving the activity of the entire world. Oceans are not passive containers. They are dynamic systems with what amounts to planetary-scale memory. They store and release heat, dissolve gases from the atmosphere above, and move nutrients from one region to another through vast circulation patterns. On Earth, life and the ocean are so deeply intertwined that separating the history of one from the history of the other is essentially impossible. The same underlying principle could apply to a very different ocean on a very different world, even if every observable detail were alien beyond recognition. The chemistry tentatively identified in this atmosphere continues to suggest that active and complex processes may be at work. A world without life tends, over sufficiently long timescales, toward chemical equilibrium. Reactions run their course. The atmosphere settles toward a stable and inert configuration. Life disrupts that tendency in a measurable and persistent way. It consumes, releases, transforms, and renews in continuous cycles that prevent the atmosphere from ever fully settling into the equilibrium that chemistry alone would eventually produce. This is why the possible detection of dimethyl sulfide generated such extraordinary excitement. On Earth, that molecule is closely and reliably associated with biological activity, especially with communities of marine microbial organisms living in the surface waters of the ocean. It rises from living seas like a chemical record of ongoing metabolism, a byproduct of countless tiny living organisms shaping the chemistry of the air above them. If something functionally similar is occurring on K2-18b, the atmosphere stops being simply a weather system operating through purely physical and chemical laws. It potentially becomes evidence of an active exchange between processes happening in a hidden ocean below and measurable gases floating in the atmosphere above. For most of human history, the universe has felt like a space of overwhelming and fundamental silence, beautiful, vast, and essentially empty of anything that might respond to our questions or our presence. Every culture that has ever existed on Earth has asked some version of the same question through whatever intellectual framework was available to it. Are we alone? Every generation found its own way to approach that question, but none could compel the universe to provide an answer accessible to human instruments. The stars remained unreachable in any practical sense. Their light arrived, but the nature of the worlds they might carry did not. Then, slowly and with gathering acceleration, that began to change. Not through a spacecraft breaking through the atmosphere of another inhabited world. Not through a signal broadcast across the radio spectrum in deliberate mathematical patterns. Not through any face looking back at us, through the darkness with recognition. The change came through chemistry, through the microscopic distortions that atmospheric gases produce in the light of distant stars, through the realization that an atmosphere floating above a planet more than 100 light-years away can carry the chemical signature of processes actively occurring on that world. Fiction tends to give us contact as a dramatic and sudden event. Reality appears to be delivering something more subtle and more lasting. An accumulation of chemical knowledge slowly read from ancient light that has traveled across an almost incomprehensible distance to reach instruments that barely existed as concepts a generation ago. What makes this discovery feel so significant is that it is not really about one planet orbiting one obscure red star. It is about a threshold in human awareness of what the cosmos might contain. For centuries, the possibility of life beyond Earth belonged entirely to philosophical debate and imaginative speculation. It was an intuition, sometimes a hope, and for some a deeply held conviction. But it could not be approached through measurement. Now, for the first time in human history, the question is beginning to migrate from the realm of pure imagination into the domain of actual instrumentation and measurable chemistry. We are analyzing real atmospheric spectra from real worlds at real distances. We are tracing the signatures of real molecules in real light. The search has become physical in a way it never was before. Every significant advance in scientific understanding has in some way repositioned humanity within the larger context of reality. The recognition that Earth orbits the Sun reduced our planet's apparent cosmic centrality, but expanded our understanding of the actual solar system. The realization that human beings are one branch among countless others on the evolutionary tree of life connected us biologically to everything that has ever lived. Modern cosmology revealed that our galaxy is just one structure among hundreds of billions in an observable universe of staggering scale. Each of these discoveries reduced a particular illusion of centrality, but each also enlarged our genuine sense of belonging to something vast and ancient. We were not made smaller by those discoveries. We were placed more accurately within the context of a reality far greater than previous generations had understood. This moment may represent the next step in exactly that same long process. If life exists on another world, even in the simplest microbial form, then biology itself stops being a private event confined to one planet. It becomes part of the fabric of the universe, not necessarily common everywhere, not necessarily intelligent or technologically capable, but real beyond Earth. Once that boundary is genuinely crossed and confirmed, the meaning of existence expands in ways that touch every dimension of how human beings understand themselves and their place in the cosmos. Over the coming decades, the evidence will accumulate. What now feels like a fragile and exciting possibility may become one of the defining confirmed truths of modern civilization. A truth that changes not just what we know about the universe in a technical sense, but how we understand ourselves within it at the deepest level. Because the real meaning of a discovery like this does not live in any single data point or statistical confidence interval. It lives in the slow and quiet transformation it produces in how we see the night sky above us, how we understand the nature of life and its relationship to the physical universe, and how we conceive of our own position within a cosmos that may be far more generative and far more alive than we ever allowed ourselves to seriously believe. K2-18b may be only the first distant world to make that possibility feel genuinely real rather than merely theoretically interesting. It will not be the last. Other telescopes are being designed and built with increasing capability. Other atmospheres will be analyzed with ever-improving precision. More worlds will transition from the category of anonymous points of light into candidates with measurable atmospheric properties and compelling chemical stories. Some signals will weaken under scrutiny and fade into noise. Some interpretations will require substantial revision. A few may grow stronger and more convincing with each additional observation until they harden into something approaching confirmed scientific fact. The stars are still very far away. They remain beyond the reach of any technology we can currently envision sending to them in any reasonable time frame. But they no longer feel entirely silent in the way they once did. A sky full of stars used to communicate, above all else, a sense of magnificent but unreachable distance. Now it suggests a different kind of potential. Each faint point of light can no longer be dismissed with complete confidence as simply another burning sun surrounded by empty darkness. It may be the gravitational center of a planetary system with worlds of its own, climates of its own, and perhaps even biology of its own operating beneath alien, of clouds we have not yet learned to see. And in that small but genuinely profound shift in how the cosmos presents itself to human awareness, something important about our relationship with the universe has already changed permanently, whether or not we are fully ready to recognize the magnitude of that change just yet.